Hey everyone, I just wanted to record a short video on some hints for certain problems on homework 0, and hopefully seeing how I think about these problems will help you guys. I take sort of a visual approach. I think it's useful. So let's start with a problem that is similar to the ones we see on problem 4. Not exactly the same, but so suppose that I have this summation, and let's just call this is the answer to the problem. We are looking for ways to write this expression using matrix quantities for C and B. You can tell they're both matrices because they contain pairs of indices. So if one of them had a single index, then that would be a vector, but they have double indexes both, so they're matrices. And so we want to write this expression in terms of those matrix quantities. And now this expression, though, this is just a scalar. So really, this is going to be finally written as one element of some matrix that we're going to derive. And we'll see there's actually a couple different ways we can approach this. So maybe let's just start out what I think would be the easiest problem from the way this is written. So let's imagine that we have matrix B. So the way that matrix B is defined here, you can see that I is the row index and J is the column index. So what I like to do is I like to draw a little arrow that shows the index. So I goes along that dimension, and J goes along that dimension. Now this quantity is being multiplied by C, and we want to write C on the left here because I is the summation index. And so when we do matrix multiplication, essentially it's like this inner dimension here, that is what we're summing over. We're doing this times this, plus this times this, plus this times this, and so on. So that is a sum over I. So what that means is that I has to go along that direction, along the columns of the first matrix. And then when we look at C, there's only one other index, which is K, so K must go this way. Okay, now when you look at this matrix on the left is a little bit different than just your plain C matrix, because the plain C matrix has I as the row index, whereas here I is going across the columns. So what we really have on the left is we have C transpose. Because when you transpose a matrix, you're essentially swapping the rows and columns. Okay, so at the end of the day, this matrix multiply is essentially doing the kind of operation we see here. But there's one other key thing here. As we said before, this is a scalar, and you can see that the value of this scalar depends on our choices for K and J. I is sort of what I like to think of as a dummy variable or a temporary variable. Once you execute this sum, there's no more i's, but there does remain a K and a J. So, so that is sort of visible here. K is going to tell us which row of this matrix we're looking at, and J is telling us which column we're looking at. So putting this all together, we have the matrix C transpose B, right? That is a single matrix. And we are now going to be looking at the row K, column J of that. So, sorry, maybe I should write, so this is the answer that we have above. So this implies that this is the answer. Okay, so this is one way to answer this question. And let me write some underlines under those quantities to help us remember that these are in fact matrices. Okay, so there's another way we can do this also, and one of the ways we can see that is, remember that if I have scalars, multiplication with scalars commutes, so I can reorder that. Now, multiplication with matrices does not commute. So like C transpose B is not the same as B times C transpose. Okay, so we have to be careful when we work with matrices, we don't change their order, but when we work with scalars, we can freely change their order. So I can rewrite the sum as Bij Cik, and that might suggest that I somehow formulate an answer here where C is on the right. And once again, notice that we're summing over I. I is one of these inner dimensions because of the way that C is defined. Right? So we have here I goes down the rows, C across the columns, so that's all good. And now, from the way this is written, this suggests that I want something to do with B on the left. We can do that, but we have to be, again, careful. So the way that B is defined on its own, we see that I comes down the rows. But we actually need that I goes across the columns in order to match the other I. So I'm going to put I going this way across the columns, and then therefore the other index, which is J, that's the one that must go down the rows. And so what we really have on the left is not B alone, but it's B transpose, because B transpose has J going down the columns and I across the rows. So I can put B transpose here. Okay, so all of this implies then that I'm looking at this new matrix, B transpose C. But once again, we have to be careful about what index are we extracting to give us this answer, or maybe this answer. And we're looking at the jth row and the kth column. So this is jth row, kth column. So this is another way to write the answer. And maybe the final question we might ask is, does it make sense that there's two ways to write the answer? In other words, is this actually equal to this? And the answer is yes. So again, remember that if I have a matrix X, and let's say I start out and define X as perhaps with K going down the rows and J across the columns. So I'm pulling out this entry of X. Well, we know that this is the same thing as pulling out from the transpose X the jth row and kth column. And so comparing this to this, we can sort of ask the question, well, if this is X, then is this X transpose? And the answer is yes. So starting here, if C transpose B, let's say that's matrix. If I want to transpose that, let's remember what happens. So when you transpose a product of matrices, two things happen. You transpose the individual matrices, but also you reverse their order. So transposing that gives us B transpose C. And so essentially, we can finally see that this all makes sense. So this matrix is the transpose of this one. And so it makes sense that when you rearrange the two indices, you get the same thing. So these are both equal to the answer. So basically, all of that is good. All of that is self-consistent. And so hopefully this sort of clarifies how you can answer questions like you find on problem 4. Now the ones on problem 5 are actually, I would say, an extension of this. They're taking these ideas and then just going a little bit farther. And so let me write down an example of something that's like what we have in problem 5, but a little bit different. In fact, maybe even a little bit more complicated. So let's suppose that my objective is to take this new expression. So I'm going to sum over k, and then I'm going to have another quantity summed over I, which is going to be Cik Bij, that thing squared. Okay, so I'm choosing this in order to be able to build off this previous answer, just to kind of shorten the video. And so we have already deduced that this quantity here can be written in a couple different ways. It can be written like this or like this. So let's just say I choose one of these arbitrarily. So maybe I'll start with the first one. And so what I can do is I can rewrite this as a sum. Let me just maybe substitute this. So we have C transpose B, that matrix, I'm extracting the kth row and jth column. Okay, so now you can see what we want to do is you want to take this, but then do some further stuff to it and write that concisely in terms of matrix vector quantities without any summations. Okay, so let's just go step by step. So we have the sum over k, and now I have this quantity squared. So what I could do is I could just write that quantity times itself. So I have that quantity times itself. Okay, now you can see that this is sort of looking like one element of a matrix-matrix multiplication. But again, the thing we have to look out for is we want that k is on the inside. It's the inner index of a matrix multiply. So one way we could do that is we could use this one as is, but then transpose this matrix, which has the effect of swapping these. And so in other words, I could rewrite this equivalently as B transpose C, extracting jth row and kth column, multiplying this matrix kj. And if I want to draw a picture of this, I would draw it as follows. I have this matrix B transpose C, and oh, sorry, this reminds me that I forgot to underline those above. Okay, sorry about that. Okay, so so now I have B transpose C, and you can see J is coming along that dimension, K this way, and then on the right I have C transpose B, K along the inner dimension down the rows, J across the columns. And so now you can see that, yes, this K is really doing a matrix multiply. So at the end of the day, what we have here, I can rewrite this as this new matrix, which is B transpose C times C transpose B. And I am extracting one particular entry from that, and I'm looking at the jth row and the jth column of this new matrix. So I have J, J there. So finally, what I've done is I've taken this thing which has two summations, and I've written it in terms of the matrix quantities without using any summations at all. And this sort of thing is very useful in a lot of the lectures and homework assignments and labs and so on that we're going to have later in the term. So hopefully this has been useful to you. You'll see me drawing these kinds of pictures in the lectures sometimes, but I think it's a nice way to go to visualize what's happening. And if you use this approach, you can really handle arbitrarily complex expressions just by kind of taking it step by step, writing it out, and deducing the final answer. All right, hope this was useful to you.